So how happy am I? Here I am, towards the end of August. Should be on my summer holiday, but I'm quarantining because I was a bit too late getting back from France. So for that very good reason, I've decided to make you some independent study videos that hopefully should keep you going till at least half term. So one of these a week. Now, the first one we're going to do is all to do with exponential modelling, which we sort of covered in the very last video of chapter 14 at the end of last term for pure maths, but it comes into now into statistics, which is what we're going to be covering in these videos. So hang on to your seats and get a load of this. Now there are two kinds of exponential models. So when we're talking exponential, we're talking about things to do with either growth or decay, which is why they come up in statistics, because we get into some real life stuff which is all complicated to look at, and it's about making it not complicated. That process is a little tricky at first, but it will allow us to draw a straight line graph. Now there's going to be two kinds of ways in which this exponential growth can happen. It can happen where our variables y and x are in this relationship, and it can also happen where our constants are multiplied together and then one of them is to the power of x, and it's what to do in both scenarios that's important. So I thought I'd talk it through this way because I don't think the way I did it last time was all that clear necessarily, so hopefully this will be a bit better. So what you do is you've got to think, I'm going to take logs of both sides to rationalize this whole situation. So if you did that, that would look like that for that one, and it could look like this for this one. So we're just taking the logs of both sides. Now I think before we jumped straight into these sides all being broken up, but you may not have seen sort of y, and it's all about using log law. So the log y side is going to stay the same each time, and it's going to leave that on its own. But because we're multiplying, the multiplicative law would say that because a times x, log a times x, that means that we can add together those logs. And this all comes about because of, with power law, when you multiply two powers, you can add the powers. It's all to do with that. So we can say that that becomes log a plus log x to the power n. And this one over here, we can say that becomes log a plus log b to the power of x. And then the last thing that we're going to do is we're going to use our power law on that part. So the log a we've already sorted, that is log a, but this means that we're going to have n many of log x, so this can become n log x. And that's important because if you plot log y against log x, you're going to end up with this being your y-intercept, log a being your y-intercept, and however many log x's you've got being your gradient. So that n is going to be our gradient. When we come over here and do the same thing, the only difference is that we've got x multiplied by log b. And that means that this time, if we plot x against log y, log b is going to be what we're timesing x by, so log b becomes our gradient. Right, so what's that ultimately? So what we're saying is that the log y, so this is always log y down here, log y is equal to that, and following all the way down there. So on this side here, if we've got information like this, we can plot log y on the y-axis, and we can plot log x on the x-axis, and we'll get a straight line for our information where the y-intercept is log a and n is going to be the gradient. And over here we're going to have the same thing on the y-axis because we've got log y there. Going along the bottom, it'll just be plotted against x. because x is being multiplied by log b, which we can do there. So the gradient is going to be log b, and the y-intercept is still log a. And how do you remember that? Well, you remember it by going through this little process at the beginning each time and just thinking it through. But you'll quite quickly get used to it. Basically, you've got to have the log involved with the x somewhere. If you've just got log y against x, then the gradient is going to be the log of the other constant. Whereas if you've got log y against log x, that x is going to be time or whatever, then your gradient will just be what your time's in the log by. So the logs get involved once each time. And what you've got to do is just work out which one of these situations you're looking at, and then it's always the same. Now I'm going to do just one example and then give you a few to have a go at, and I'll go through the trickier question of those at the beginning of our next video. Okay. Here's our example. I'm going to read it to you, even though I know you've been doing your own reading for some time now. So what we've got is, it says some data is collected on the temperature in degrees Celsius. And if you look in the textbook on page 2, they've actually got the data written out, but you don't need it. So some data has been collected on the temperature of a colony of bacteria, T, and its growth rate, G. The data are coded using the changes of variable x equals t. So we've got the size of the colony going along the x-axis, and y equals log g. So the log of the growth rate is going up the y-axis. The regression line just means line of best fit, really, of y on x is found to be y equals negative 0.2215 plus 0.0792x. So that's just like y equals mx plus c is a straight line. Now the first question, you want to copy this down, is that Mika says the constant negative 0.2215 in the regression line means that the colony is shrinking when the temperature is 0 degrees. Explain why Mika is wrong. So first of all, why does Mika think that it's shrinking? If I was just to do a little sketch here, I've got log g going up the y-axis. I've got t going along the x-axis, and the y-intercept minus 0.22, that could be about there if that was minus 0.2215, and then we would have a straight line. So there's my straight line, and the gradient of that line is going to be how many x's we've got, 0.0792. Now because this is g is the growth rate, isn't it? And that's negative. That's why Mika's saying that the colony is shrinking at the beginning, and the beginning is when the temperature is 0, because we're talking about degrees Celsius there, aren't we? So that's why he thinks it. But why is it not? It's because when we've got something that's been logged, it's not that is the growth rate. Log A is equal to minus 0.2215. So the reason why is the log of the growth rate is negative 0.2215. And this means, because whenever you've just got log written, that means log of base 10, doesn't it? This means the real growth rate at 0 degrees C is going to be 10 to the power negative 0.2215. Now at that moment, I need to get the calculator out, and if I do 10 to the power negative 0.2215, it just means that the growth rate is going to be less than 1, doesn't it, if it's a negative power? It's 0.6, which means it's positive, which is positive. And then we've answered that question. Okay, now this is the last part of the example, a really crucial bit. So copy this down. You might want to pause the video at this point and have a little go at it before I explain it for you. So I've written out the equation we had at the beginning again of the coded data with the y, where y is log g, isn't it? Given the data can be modelled by an equation of the form g, so that's not log g, but g equals kb to the power t, where k and b are constants, find the values of k and b. And this is where we need to start thinking about what we were talking about at the very beginning, which is taking the log of both sides. So if I take the log of both sides here, if I take the log of both sides of this, so g equals kb to the power t, log g is going to be log kb to the power t, and then we were saying that multiplicative law, easy for me to say, means that we can add those two that have been multiplied together, and then power law means that we can rewrite this, and the only way to get good at this is by practicing a load until it becomes something that you do just as a natural thing. So we've got log g is equal to that. Now that is what's being represented by our formula, so I'm going to write that out again underneath, and because that's when it starts to become that little bit easier. First thing of all is, this is the easy part, the y-intercept, because that's always going to be this log here. So for the y-intercept, we know that that is log k. So I'm going to write that up here as I've got a bit of space. So therefore, log k is equal to negative 0.2215. And once I know that, I know that that means that k is going to be 10 to the power of minus 0.2215. Put that into the calculator, and that's what we did actually a minute ago, wasn't it? We can say that k equals 0.600 to 3 significant figures. So that's k. And then the other part here is 0.0792 is the gradient, isn't it? Now we were plotting x as t, it wasn't as log x, was it? So that means that this must be log b. So t has become x, because that was what was going along on the x-axis, wasn't it? So this log b is our gradient. So gradient equals log b. The gradient is 0.0792, and therefore I can say that log b equals 0.092, and b must be equal to 10 to the power 0.0792. And if you put that into the calculator, you get 1.200. So you can say that b is 1.20 to 3 significant figures. So that means the growth rate is going to be that. Okay, now that is everything that we've got so far. So all we need to do now is for me to tell you which questions it is that I want you to have a little go at. And if you go to exercise 1A, have a go at questions 1, 2, 4 and 8. Give them a really good go. I will put the answers up as well as the questions in a moment at the end of this video, but I will also go through my worked solution for number 8 at the beginning of next week's lesson, which you can find in the usual place. Okay folks, I hope you enjoy all of that. Cheerio for now.